Okay, so when we're talking about related rates, we're going to be talking about quantities where we've got two things that we're measuring, and they're both changing in relation to another variable. Normally, that third variable is going to be time. So when we're taking derivatives, we're going to be taking derivatives with respect to time. So instead of dy dx, it will be dy dt. Okay? So that's what our derivative will be. Anytime, how do you recognize these types of problems? Anytime you see something with a d something dt, it's probably going to be a related rates problem. Anytime you've got two or three things changing, it's probably going to be a related rates problem. And we're going to work through several different types of those here today. So the best way I know to do this is just kind of jump right in. This is kind of a contrived problem here. Suppose x and y are both differentiable functions of time, t, and are related by y equals x squared plus 3. There's our equation. There's the relationship between y and x. We know that dy dt is, we want to find what dy dt is when x is 1, given that dx dt is 2 when x is 1. So this is what we're looking for, dy dt. How do you think we should find dy dt? Into what? Okay, so we get y equals 1 plus 3, so y equals 4. But that's not dy dt.
But we know that 1 over dx is 1. Find the derivative first.
We first of all need to find the derivative of this equation. Now that's a crucial point. The first thing you need to do is to derive it, okay? People say, well, why can't I solve it first and then derive it? What's dy dt now? If we look at this, dy dt is 0. But we know it's got to be changing. We're already told that they're changing. So we've got to derive it first. So if we're taking the derivative of y equals x squared plus 3 with respect to time, we get dy dt equals 2x dx dt plus 0. Now, why did I have to put a dx dt in there? That's right. We're taking derivatives with respect to t. What's the formal official name for this then? What kind of differentiation are we doing here? Anybody remember? Implicit differentiation, okay? So everything you do with related rates is going to be implicit differentiation. So now we have an equation, dy over dt equals 2x dx dt. We know that x is 1. We know that dx dt is 2. So we are looking for this, dy over dt equals 2 times 1 times 2. So dy dt is 5. Okay? Now that's, as I said, that's just a very contrived problem. You won't see but maybe one or two of those all year. Most of the time we're going to be focused on, let's make it 4 instead. I'm not doing good with my numbers this morning. It's Monday, yeah. Y'all have to check my numbers. I'm kind of rough with those sometimes. So yes, let's make it 4 instead. So if you want to think of this, if this were sprockets A and B like we looked at a while ago, that would mean for every 2 times this one goes around, that one goes around 4 times. But most of the time, most of the things, bless you, we're going to deal with are going to be something that we don't like. It's going to be word problems. They're going to have words. You're going to have to come up with your equations, and you're going to have to do all the work yourself. So I dearly love these, okay? So let's look at the next one here. A pebble dropped into a calm pool causes ripples in the form of concentric circles. Nice and soothing picture here we've got, okay? The radius of the outer circle is increasing at a constant rate of 0.75 feet per second. When the radius is 5 feet, at what rate is the total area of the water changing? Now, as you read this, you probably want to kind of use some of your rules that you approach FRQs on. You know, what's important in here? It says the radius, constant rate of 0.75. Radius is 5 feet. At what rate is the total area of the water changing? So the 0.75 is going to be what?
The velocity.
0.75 feet per second, but we don't have velocity in here. It's a rate, but what is it a rate of? The radius change, okay? So we would probably say this is dr over dt. R standing for radius. Does that make sense? Well, then we know R is 5 feet. Well, what other variable do we have in here? What are we looking for? At what rate is the total area?
So we're looking for the acceleration of the water.
No, it says at what rate is the total area changing? So we're looking for at what rate is the total area, so we must have something to do with area, but it says at what rate is the total area of the water changing? At what rate? That means we're actually trying to figure out what dA over dt is. That's what we're trying to figure out. So what's our relationship between A and R? How do you know it's pi r squared?
That's what the area of the circle is.
Yes, and how do we know it's a circle? Says concentric circles. Is concentric important? What does concentric mean? No.
No, it's like circles.
They're all circles within circles. They all have, because think about when a pebble goes into water, you're going to see little ripples out all the way. So they're all going to be perfect circles with the same center. So we've got all of our information here. We've got area equals pi r squared. R is 5, dr dt is 0.75, and we're looking for dA dt. What do you think we should do now? If we plug 5 into A, we'll get 25 pi. Is that our answer? No. We can take the derivative. Okay, we need to take the derivative of this. So dA over dt equals what? Pi 2r. Is that something else, or I'm not sure, or wouldn't be dx, dr dt. Do we need dr dt there, people? Think so? It's implicit differentiation. Everything is derivatives taken with respect to time. And now it becomes a 7th grade math problem. We plug and chug. dA dt equals pi times 2 times 5 times 0.75, which is 7.5 pi feet per second. Actually, feet squared per second.
So in this case, you do not want us using, like, actually multiplying the 7.5 by pi?
Doesn't really matter. You could, if you wanted to, multiply it out, but I would accept that as an answer also. 7.5 feet squared per second. Why is it feet squared? is 5. This is 5 feet right here. This is feet per second. So when we multiply feet times feet per second, we get feet squared. Also, how do we measure area? In square units, don't we? So dA should be something squared over dt time, so feet squared per second. Just a way for you to do some physics kind of stuff and check your units to be sure that your units are right there, okay? So is that complicated, people? You'll feel better in a few hundred of them, okay? Air is being pumped into a spherical balloon at a rate of 3.875 cubic feet per minute. Find the rate of change of the radius when the radius is 3. So think about this for a minute. What relationship are you going to have between what two quantities here? Somebody tell us what you think. Area and radius. Okay, it says when the radius is 3. Okay, so we got that. Volume instead of area, or volume also in here? No, I think it's volume instead of area. You only have to variables. Okay. So why do we think it's volume instead of area then? Cubic feet. Okay? Cubic feet right here. That's a giveaway that we're dealing with volume, okay? So then this 3.875, what is it? It says cubic feet per minute. All right? Anything that's per minute is going to be dt, but what's the top variable? Is it dr, dv? dv. How do you know that, Kevin? It's feet cubed. It's a volume rate, okay? Air is being pumped into the balloon at 0.3875. Is it a positive or a negative? Positive. Why? Oh, could it be negative?
It could be if they were like deflating the ball.
If we're deflating it, it would be negative, okay? So signs are important here, okay? So it is positive. Find the rate of change of the radius. So what are we looking for? The RDT. So we need to figure out how do we find the volume of a sphere? Who remembers that? Very good. I don't know when I've had anybody knew the 4/3 part. No. Well, she got it without it over there. Kudos to you. 4/3 pi r cubed. All right? So now, what do you think we ought to do? We've got all of our information. What do you think we should do now? Take the derivative of this thing right here. Take the derivative. So we get dv over dt equals 4/3 pi, because those are just constant numbers. We're just going to write them down. What's the derivative of r cubed? 3r squared dr dt.
Don't we already know dv over dt?
Oh, very good. We know dv over dt. So now we're going to put 3.875 on the left side of this equation, okay? Because that's dv dt. And I'm going to cancel this 3 with this 3 there and get 4 pi times 3 squared dr over dt. And at this point, if I had a handy-dandy calculator, I would pull it out and figure out what this number is. 3.875 divided by 36 pi. That's what my dr over dt is. Somebody with a calculating device, please figure out what that is for us. Did I do that wrong? No, I didn't. Yes, sir.
Where'd the radius go?
Where did the radius?
Okay, got it.
Yeah. I didn't write it down here, did I? Yeah. See, I canceled this 3 with that 3.
I just realized that my brain.
And then 3 squared.
I
Yeah.
did that too, but my brain just got rid of the R.
Yes, it didn't make sense to me there for a minute. Okay, it does now. All right, that sounds right to me. 3.875 divided by parentheses 36 pi close parentheses equals 0.03426. Is that what you got?
Yeah, I forgot to put it in.
Yeah, you've got to put the parentheses in there. How about that? It does work. That's even more brilliant. 0.034 feet per second. All right, I have a question. Does anybody have a question about what we did there? What happened to the feet cubed?
Like, how did you get from...
All right, this would be feet cubed per second up here, right? All right, this is going to be feet squared here, isn't it? And that's not going to have any signs with it. So when I take feet cubed divided by feet squared, I get down to just feet. Now, don't think about the math for a second. Think about real life. You're blowing up a balloon. As the balloon gets bigger, does dRdt stay that number? Does dRdt get bigger? Does dRdt get smaller? Real life, not the math. The more you blow into it, the balloon's already yay big. Is dRdt, is the radius going to increase at a faster rate the more you blow in there? The same rate or a slower rate? Slower? Is that what you said? Slower? No? Slower. Got 2 slowers and 3 thinkers. Slower, faster, the same? Or thinking? Huh? Slower? Thinking? Okay, thinker?
Well, if there's no limit on the balloon, where does that change it? Because say you get to your absolute maximum limit.
We aren't at that max yet, okay? So we're just kind of in between there, okay? You're blowing bubble gum. You're blowing a bubble with bubble gum. All of you chewed bubble gum. It's illegal to do here at school, but you've done it somewhere, I'm sure. So think about that. Slower, faster, or the same?
Wouldn't it keep increasing exponentially as the thing gets larger?
So you think dr is going to get slower, get bigger, faster? I don't know. We got 3 slowers. I heard her faster. All right, now let's do something real simple here. Let's take this problem and change the radius to 5 feet. So what does that change down here in our final answer here? This 36 is going to become 100, right? So now we've got 3.875 divided by 100 pi. So it's going to be smaller. Okay? So, because think about it. When you've got the flat balloon in your mouth and you blow, what happens? Poof. Yeah, but assuming you can hold on to it, okay? It's going to go from flat to poof real quick. And then you're going to take another breath and blow in, and you're going to see it. And after it gets to a certain size, you blow in air, and it doesn't look like it's going anywhere or it's not moving as fast. So the more air you put in, it's getting bigger, but the radius is getting slower all the time there, okay? The rate that the radius is getting bigger is slower all the time. All right, so let's look at the next problem. Oh, I didn't even give you a pretty picture with this one. So you're going to need to come up with some kind of picture. It doesn't have to be pretty. It does need to be a picture, though. An airplane is flying at a constant altitude on a flight path that will take it directly over a radar tracking station. If the distance between the plane and the tracking station is decreasing at a rate of 300 miles per hour, when the distance between them is 13 miles, what is the speed of the plane? So let's get us a picture here. Okay, we've got an airplane. Okay? And we've got a tracking station. So the airplane is flying a flight path that will take it directly over the tracking station. So he's headed this way. And I know that's not a straight line, but let's believe it is, okay? Now it says the distance between the plane and the tracking station is decreasing at a rate of 300 miles per hour. What on earth does that mean?
Every mile plane travels, the distance between the tracking station and the airplane is like 300 kilometers.
Right, okay, so now, what do we mean by the distance between the plane and the tracking station? What line is that? Is that this line? Yeah, she says hesitantly.
Isn't it a vertical line?
It's this line? This line? Which one do we think it is? A? Is it this line? Which line do we think it is? Is it the horizontal line, the vertical line, or the diagonal line? If we say the distance between the plane and the tracking. The distance between the plane and the tracking station. If I said, what's the distance between Connor and I, or if I said the distance between Connor and I are 10 feet, what do you think that means? What distance do you think that is? Do you think that's going down to Chase and then over? Do you think that's a straight line there, okay? So the distance between the plane and the tracking station should be this line right here. I'll call it S, okay? Let's call that S. So now, what is ds over dt? Sarah Beth wrote down negative 300 miles per hour. What do y'all think? Why negative? Decreasing, okay? So ds dt is negative 300 miles per hour. What is the speed of the plane? What's that asking for? In terms of our line segments there. It's asking for, the speed is going to be in miles per hour. So we're asking for either, let's call that A, and let's call that B. We're either trying to figure out dA over dt or dB over dt. Okay, so we're being asked to figure out what dA over dt is. And what did you say about a constant? What is it? Okay, it's flying at a constant altitude. What does that mean? Same height. So is that dB over dt is a speed over here? Right. No, dt. So B is a constant number. So dB over dt is 0. Now, do we know what that constant number is? No, we don't. Okay, so it doesn't really matter. Hopefully. So what relationship is there between S and A? Very good. A squared plus B squared equals S squared. Do y'all see that? Because if B is a constant number, then I could take this line segment right here and move it over here, and now I've got a right triangle, okay? We could think vectors too, but we don't say vectors in here very often. So A squared plus B squared equals S squared. So what do we need to do now? We've got a relationship. We've written down a bunch of stuff. Let's find a derivative. So we've got 2A dA over dt, right? Plus 2B dB over dt equals 2S ds over dt. Now, I want to make our life easier here. Would everybody agree to throwing away the 2's? Why can we do that? There's a 2 in each one of them, so we're going to take away the 2's. And now let's put in what we do know. Okay? We don't know A, it doesn't look like. We don't know dA. We don't know B. We know dB is 0, so that thing's going to go away. We know S is 13, and we know ds is negative 300, right?
I thought A was 13.
Is A 13? When the distance between them is 13 miles. Now remember we talked about, we said this, it says, all right, let's see. If the distance between the plane and tracking station is decreasing at 300. So we said this diagonal line was the distance between the plane and the tracking station to get our ds over dt. When the distance between them, again, that's got to be talking about the same line. So I think the 13 has to go there. So does anybody see a problem with what we've done so far? The only problem, that's right, the only problem I see is we've got negative 3,900 over A, and we don't know what A is. Any ideas on how to find A? Can we find A? I don't see enough information to grab something here. I don't think we can figure out what A is right now. So I think I needed to give you more information on this problem here. Let's say that A was 12 miles. Okay? I'm just poof making that up there. If A were 12 miles, then instead of that we could say it's 12 there, and we would have dA over dt equals whatever that is. 3,900 divided by 12. Oh, come on. 3,900 divided by 12. But now our answer is going to be negative 325 miles per hour. Why negative? I mean, the math says it's negative. Is it really negative? What does that negative sign mean? I mean, do you really think you're looking up there and the plane's flying backwards? Be cool, but I don't think that's what you said. Very good. This negative sign here, you've got to interpret it. That means it's getting closer to me, okay? It's decreasing the distance between myself and the plane. Since the distance is decreasing, That means it's a negative 325. It's getting closer to me. Okay? All right, very good. I like that problem. I really do. Let's see, is that the one we want to do? Yeah. A camera is stationed 2,000 feet from a rocket that is being launched into space. The rocket's position at any time t can be found by the equation s equals 55t squared. Find the rate of change of the angle of elevation at 12 seconds after liftoff. Oh, Sarah Beth says it's got a theta in it, so she just wants to cry. All right, so let's draw a picture, okay? You have your rocket. And it's going upwards. And we have our camera. Camera. And it's 2,000 feet away. And we're assuming that the camera is trying to take a picture of the rocket. Find the rate of change of the angle of elevation at 12 seconds after liftoff. So, Sarah Beth, where's our theta going to be? At the camera. We're going to say that's theta there, okay?
And then your vertical is going to be 12 seconds, right? The rocket vertical?
The rocket vertical, we want to know at 12 seconds. So is this going to be this distance? All right, listen. The rocket's position at any time can be found by s equals 55 t squared. So this over here is going to be changing, right? So it's going to be the letter S. Okay? So the rocket's position at any time t can be found by s equals 55 t squared. Find the rate of change of the angle of elevation at 12 seconds after the liftoff. So we can find s at t equals 12. Sounds like we're going to need that. That's going to be 55 times 144. Somebody do that for us. 7,920. Okay, good. So now, what relationship is there between S and theta? Yeah, but we need an equation, something that we can write an equal sign in there. Does anyone see a relationship between S and theta? Tangent of theta equals S over 2,000. Oh boy, that looks like fun, doesn't it? So now what do you think we need to do? Find S. We already found S would be 7,920.
So what do we plug in our equation, like the 55t squared?
For S?
Yeah.
Okay, so yeah, we could do that. We could say then the tangent of theta equals 55t squared over 2,000. Nothing wrong with that. That gets us with just thetas and t's in there. And now we know t is 12, so we could plug it in, but that's only going to find us theta. We've got to take a derivative somewhere. Yeah. What's the derivative of tan theta? Secant squared theta times d theta over dt equals 55 over 2,000 times 2t dt over dt?
So, 2t times 1.
Yeah, are y'all okay with that? That dt over dt is just going to be 1, right? So if we do that, then we could say then that d theta over dt equals 110 over 2,000 t times secant squared is 1 over cosine squared theta. Right? Do y'all buy that? Because secant squared is the same as 1 over cosine squared. So dividing by 1 over cosine squared is the same as multiplying by cosine squared. Well, we know a t, don't we? But we don't have a theta there. Go back up to the beginning, meaning what? Which line? Okay, let's use a different color. She's saying we can figure out theta by coming right here and saying that the tangent of theta equals 7,920 over 2,000. So then we pick up our handy dandy calculator and we say 7,920 divided by 2,000. What mode am I in? I'm in radian mode, which will be okay. So I need to do inverse tan, second entry. How do I do that on here? Second tan, second answer. Answer. Is that one there? So there's my angle in radians. Now, if you did it in degrees, you didn't get that answer, but it's okay as long as you stay in degree mode. You'd be all right over there. So now we know what our tangent is. Or our angle is 1.323. All right, so we have our angle there. So we're just going to use that angle over here, and we're going to say d theta over dt equals 11 over 200. T is 12, right? Cosine squared of 1.323. Okay, secant squared is 1 over cosine squared, right? Yeah, so instead of dividing by 1 over cosine squared, I'm just going to multiply by cosine squared. So now if we pick up our handy dandy calculator, we can say the cosine of the answer squared raised to the second then times 12 times 11 divided by 2,000 is 0.00395645.
You don't need to divide by 200, right? If you figure out.
Did I divide by?
You divide by 2,000.
Oh, okay. Well, that's gonna definitely throw me off then. Oh, stink. Clear. Thank you. Y'all know more about this. I can hit delete there. Boom. Really? 0.6599? Is that what y'all got?
Oh, there's an answer in there. You change sheet and you have a different answer.
All right, so let's start all over. Let's delete that one. Let's delete that one. Okay. So now, we want cosine. 1 point. Yes, this is delta theta. Right? That raised to the second times 12 times 11 divided by 200. 0.039, and we should have done that to begin with, 0.0395. That's how big the angle is changing at 12 seconds. What about at 15 seconds? Is the angle changing faster or slower? Or the same? Why faster?
Because you're multiplying by 12 plus 15, that would be a bigger number.
That's going to be 15. But what about the fact that the angle is going to be different? Because, see, at 15, this isn't my S. So this isn't my theta. Think about it real life. Real life, okay? You're taking a picture of something that's shooting up. As soon as it leaves, what's got to happen? Think about trying to take a picture of something, okay? It's going to move quickly, and then the further up it goes, the slower it seems to go, doesn't it? So I think, yeah, so I think you're actually going to move it at a slower pace the further up. But you can, in your own time, you can peruse that and figure out what's going on there if you'd like to. So let's summarize what we've talked about today, okay? Write down what you know. Draw a picture. And then find the relationship. That's what students normally hate. Because I'm not going to give you a formula and say, this is how you do it, okay? You've got to come up with a formula. You've got to remember your area formula. You've got to remember your volume formula. You've got to remember your surface area formula later on. Then take the derivatives and plug and chug. All right? There are a few problems that you can look at for homework 17. They're not due until tomorrow night, but it would really behoove you to go ahead and look at them because tomorrow we're going to get into the more challenging problems in this realm, some things that are moving in 2 or 3 different places, two or three different ways, and talk about that some. So it would behoove you to look at some of that tonight. You've got that. You've got FRQs that you could be working on.